In the beginning of our discussion of the second derivative test last week, we gave a couple arguments as to why looking at the graph or looking at the contour diagram won't help actually derive the second derivative test. That's because no algebra is actually involved when you actually look at it. However, the conclusion we got was that if you started drawing the gradient vectors near a critical point, you A, have vectors, B, you have gradient vectors which involve the first and second derivatives formulas, which will actually help. And we can actually very clearly see from the gradient pictures whether we're looking at a maximum or a minimum or saddle point. Now, that week we had a problem where we found 4 critical points, and we classified them as maximums, minimums, or saddles. And what I want to do is just take a minute here and look at the gradient pictures near each of those critical points. So in this first one here, you can see the critical point is like right in the middle. It looks like it's going to be at 1, 1. Now if you go from 1, 1 directly north, you're going to see that you see vectors that are pointing directly away from that, right? And if you start at 1, 1 and you go right about here, now maybe here, there we go. I can just follow these arrows all the way up. There are more arrows in a different direction pointing directly away from it. Well, that's going to make this a minimum, because that says that all these gradient vectors are all pointing away from it. Very importantly, there are at least 2 different sets of vectors that are pointing directly away from it and stay on a line. Let's look at the next one. This looks like it's 1 minus 1. And again, I can see vectors pointing away. 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 In particular, I can find some vectors that point away and actually stay on that same line. And I can see other vectors that point away and stay on that same line. That's going to be very important. Let's look at this one. I think this is a saddle. If I start at the point, it looks like 0.60, right? We can see the vectors pointing east and west are pointing directly away from it, whereas the vectors north and south are pointing directly towards it. But you can see the ones that are pointing directly towards it are actually staying on that line and pointing directly towards it. And the ones that are pointing directly away from it, east and west, are actually staying on that line and pointing directly away from it. That's going to be very important, that when we have a saddle point, there are going to be some vectors pointing directly towards it. There are going to be vectors pointing directly away from it. Let's look at this last one. Again, what we have are vectors. Well, what kind is this? Right, I see vectors pointing directly towards it from the east and the west. I see vectors pointing directly away from it towards the north and the south. That's going to make this a saddle, right? That says that if we chop from west to east, we're heading toward a max, right? Because from both sides, the vectors are actually pointing in the highest direction. And in north and south, it looks like we're heading towards a min. Right, so that's going to make this a saddle. But again, it's very important that we can find some vectors that are pointing directly away from it, and we can find some vectors that are pointing directly towards it. That's when it's a saddle. What we're going to do next is go to the whiteboard and start to draw some conclusions about this.